All right, so just a quick announcement. I've made some updates to the project. So if you've already printed out the project description, you should print it out again. The changes are basically more details for you in terms of laying out your transistors, the maximum inductor size, and then also more clarification on the specs. So if anything, things have gotten easier for you, not harder. So don't worry too much. One restriction is the largest inductor you can use with a Q of 6 is 10 nanohenries. Above that, you've got to live with a lower Q. The other restriction, the other clarification is the IP3 and IP2. The spacing for the tones has been specified, and that makes it a lot easier to meet the specs. The bandwidth and gain flatness is also now part of the specification. Okay, any questions on the project? Yes.
So, like when finally you say it has to be a 2 milliwatt design,
Yes.
like how do we measure the power? Is it just the total amount of DC current that is being drawn from the 1 volt band gap supply?
Well, total power being drawn from the supply voltage plus, and so the band gap is not your supply. The band gap is a reference. And in fact, I make a clarification. So you can assume you have a current source that is referenced to a band gap, and you can mirror that to set up all your currents. The total supply, so the total current will be your LNA current, your mixer current, both mixers, plus the LO power. So you have to take that into account. So if you're using a square wave to drive your LO, you should count the CV squared F power to drive the LO. If you're using a tuned circuit, you should specify how much power that tuned circuit would dissipate. So I want to make sure the LO power is part of the spec. Otherwise, you could just use a huge transistor, and you basically get really good conversion gain and good performance, but it would require 100 milliwatts to drive the LO port. So I want to keep things realistic. Okay. Other questions about the project? All right, so let's summarize what we did last lecture. So last lecture, we wanted to have basically, we used the feedback approach to find the conditions under which an oscillator will basically become, a circuit in general will become unstable, more specifically a tuned circuit, how we could place its initial poles in the right half plane so that any kind of disturbance in the system would cause these poles to ring and grow in amplitude. And then we also at the very end discussed how eventually these poles, we hope, will saturate. In other words, the growth will saturate and will reach a steady state. So we talked about this startup region where the circuit grows exponentially, and then we talked about what happens in steady state. Okay. Pen is too thick. All right, so this is the startup region. And this is the steady state region. Okay. Now, we made the observation that to start up, basically, so our startup condition is that the initial loop gain, which is we showed as GM times R tank divided by N, where N is the feedback factor, has to be bigger than 1, right? Last lecture we showed that if this condition is true, the poles are in the right half plane. The other condition that we found was that in steady state, the large signal loop gain, GM RT over N, should exactly equal to 1, or identically equal to 1. Okay? And we found that these two conditions together tell us what the steady state oscillation amplitude is going to be. And let me search for a better pen for today. Okay, so let me give you guys another perspective on this steady state behavior. Let's call it the energy balance perspective. So let's say so the observation is if I'm in steady state, I have a tank with some resistance RT. And let me assume that somehow or another this is in steady state. And this is my active device hooked up across here, either with feedback or somehow I've connected up an active device here. So what I could say is that the power lost, let's say the power dissipated into the tank, which is V squared, the oscillation amplitude squared, divided by 2RT, that has to be balanced by the power supplied by the active circuitry, right? So in steady state, the power dissipated has to identically equal to the power supplied. So this is the average power dissipated, this is the average power supplied. Now the power that the active device actually supplies can be bursty. It can basically supply bursts of energy into the tank, but on average, that energy has to average out to the power that's being dissipated in the tank, right? So what's the power that's being supplied by the circuit? Since this voltage across here is VO, if I knew the, let's say, first harmonic current, I omega 1, coming out, this would be the power being supplied. So here I'm assuming a high Q tank. In other words, the higher harmonics of this active device see this capacitance, and that's reactive energy. So they're not actually supplying energy to the tank. We're assuming that the only energy being supplied to the tank is from the first harmonic. Okay? Now this assumption is very close to what we said last lecture when we assumed that the output was sinusoidal, and we used the concept of the large signal GM. Okay? Any questions up to here? All right, well, invoking the concept of large signal GM, this is just GM times the input, where the input is some internal terminal which is derived from the output, right, through feedback. So I could say that the input is the output divided by N, where this is the feedback factor. And I'm assuming that the input is in phase with the output after being multiplied by GM. So if GM were negative, like a normal transistor, then the feedback would have to be negative as well. Otherwise, you can see immediately that this won't work. It won't be able to supply power to the circuit. So to keep this quantity positive in the sense that if we define the current coming out as being positive, so this is I omega 1, then you can see immediately that GM times V in has to be positive. Okay. All right, well, this is the power. So the power being supplied is V out squared 2N times GM, and the power being dissipated by the tank is V out squared over 2RT. And so we see that V out drops out, factor of 2 drops out, and we have an equation GM RT over N is then therefore identically equal to 1. And this is the same equation that we derived last lecture, but now through a different perspective. So if this condition is satisfied, then we have energy balance. Okay? Questions? Yes, David?
How close is a voltage waveform close to the ideal sinusoidal? Do you have a damping on RT and also have...
Yeah, the way you can estimate how closely this is sinusoidal is you calculate how much power flows, let's say, in the second harmonic voltage. So the second harmonic voltage will be the current, basically, the impedance at second harmonic is essentially 1 over 2 omega naught C, right? And compare that to RT, you can see how much lower the impedance is at second harmonic, and that can give you a way of calculating. Okay? Yes, Debo.
So like this condition implies that the poles initially can go into the right half plane, but when a steady state is reached, they will again come back to the imaginary axis.
Exactly.
So is there any intuitive way to understand that why should the poles again come back? Like, can't we have any circuit with the poles permanently in the right half plane?
No, and we'll talk about that more today. So we'll go back to that linear circuit perspective just to gain some intuition. The reason the poles, just quickly to answer your question, then we'll talk about it again later in the lecture. The reason the poles move is because as the amplitude grows, the GM of the circuit goes down. And that means the loop gain goes down. And as the loop gain goes down, the poles tend to move back into the left half plane. Okay? All right, well, this equation also is a recipe for calculating the output amplitude, because GM is a function of the oscillation amplitude, which has to equal to n over RT. Since n is fixed and RT is fixed, then we find at what oscillation amplitude GM is equal to n over RT. So if I were to plot just GM versus VO, it might look something like this. And at some point, it's equal to n over RT, and that would be the oscillation amplitude. Okay? Now, the way we did this last lecture was we actually related this to the initial loop gain. So this is just another way of doing it. We know that GM RT over N is the loop gain, and we know GM RT over N, capital GM, is equal to 1. So if I take the ratio, it says that GM over little gm is 1 over the loop gain. So this is an alternative way of calculating the steady state amplitude. For a BJT device, capital GM over GM, little gm, is basically, I have that here, yeah, it's 2I1B over B I0B times QIQ over KT. Actually, it just simplifies to I1B over B I0B. So these are functions that you can plot in Mathematica, or let's say MATLAB, or whatever program you like. I don't want to get sued by one of these companies saying you played favoritism. But Mathematica happens to be my favorite. But you basically can plot this function. And remember, B is the input normalized to KT over Q, which is basically the output divided by N, KT over Q. Okay? So now you guys have the recipe to go home and design a BJT-based oscillator, because these functions are well known. For any other kind of oscillator, all you have to do is generate one curve, which is a large signal GM versus the oscillation amplitude, and you have the recipe essentially for determining what the output amplitude is going to be. Okay? Question?
Yeah, I don't see how you simplify and then get rid of the Q over KT.
Okay, so I just copied from my notes so we can double check. So GM is I omega 1 divided by V input. I omega 1 is basically 2I1 B, if I remember correctly, times IQ. And V input is B times KT over Q, right? So this is basically 2I1B over B times GM. So I guess I'm missing an I naught B here. Yeah, the reason, so actually this is a little tricky. Where does this I naught B come from? This assumes that I'm limiting the current. And then that gives us Gm over Gm 2 I1B B I naught B. Okay? So there's an important distinction that we made when we talked about mixers, that if you limit current, implies that I omega, let's say n, is 2 INB over I0B. If you don't, times IQ. If you don't limit the current, then it's the harmonic actually is just the Bessel function, not normalized to the 0th order. Okay? Any other questions? All right, so now I want to talk about where so this is how we reach steady state, but why is the amplitude of oscillation, so let's ask the question, why is oscillation amplitude stable? And a graphical way of thinking about stability is to think of the analogy of having a ball in a bowl, right? If I put this ball at the bottom of this bowl and I basically try to move it, if I give it a little force, I know it'll oscillate back and forth, but because there's loss in the system, it'll decay back to this point. On the other hand, if I put, let's say, a marble ball on a top of a hill like this, and I just push it a little bit, it's going to roll down the hill, right? So this is an unstable system, and this is a stable system. Now, applying the same kind of intuition to our oscillator, it's going at some fixed amplitude, and as we talked about last lecture, I'm going to disturb it. Let's say I inject charge into it, and then I'm going to watch what happens. And if it comes back, if it actually decays back down to its initial amplitude, this is, let's say, the final amplitude, this is the initial amplitude. If it comes back to the same initial amplitude, then I can say that the system is stable. Okay? Now, the reason that this happened is actually related to Debo's question. So, let's use our root locus to gain some intuition. So, we know from our root locus that for a second order system, the poles lie on a circle, right? And our initial poles, so these are the initial poles, are in the right half plane because the loop gain is bigger than 1, right? But at any given time, the loop gain is Gm VO as a function of VO RT over N. And we know that if we limit the current of a bipolar, it tends to compress. So as the oscillation amplitude gets bigger and bigger, the Gm gets smaller and smaller, right? So Gm as a function of VO goes down as VO goes up. That means that as the system grows, as the amplitude grows, the poles move to the left. And when they hit the j omega axis, loop gain is exactly equal to 1, and they just stay there. Because once they hit the j omega axis, the poles don't grow and they don't decay. So they just remain constant, right? And so that gives us some intuition for why no matter where we start in the right half plane, they just keep moving left until they hit that j omega axis. That j omega axis is a steady point because the amplitude doesn't change anymore. And there's perfect energy balance occurring there. Well, what happens if I somehow or another disturb the system, right? Let's say the disturbance causes the poles to move to the right half plane. Well, that we already discussed. So if somehow the poles move to the right half plane, there's a tendency for them to move back because the amplitude gets bigger, the gain drops, and then they move back. Well, by equally, you could say, what happens if somehow they move into the left half plane? Well, that would cause the amplitude of oscillation to decay. And as the amplitude of oscillation decays, the GM gets bigger. The GM gets bigger, that tends to push the poles back onto the j omega axis. So we can see here that very much in analogy with this system here, there's always a force that tends to return you to this position. And as long as the dynamics of the system are such this is critically damped, or damped at least, very quickly you will settle back to the same point. So the key point is that there should be a force that returns the system back to this axis if there's a disturbance in either direction. Okay, Caleb?
So can the setup you showed us ever be unstable?
Can the oscillator be unstable?
The setup you showed us, the inductor feedback.
Yeah. In fact, somebody asked me last lecture, what happens if you have too much loop gain, for instance? You can get into a situation where the amplitude just keeps growing and growing, and the system just rails out, and then just dies on you. It's either supply rail. So you have to be careful when you design these systems that you simulate them over process, temperature process, and make sure that your initial loop gain is a good choice that always leads to oscillation. If you study nonlinear circuits in more general terms, you'll find that there's basically, you can think of the oscillation as being an equilibrium state. There's equilibrium states that correspond to, just from a mathematical perspective, you have your system can be described by x dot equals f of x, right? Where x is the state of the system. This could be the charges on the capacitors and the currents in the inductors. And f of x is some general nonlinear function, right? So if f of x ever equals to 0, that corresponds to x equals to a constant, right? So in the phase plane, you could say that if you ever hit one of these points, the system will just potentially, if you're exactly at one of these equilibrium points, let's call these x01, x02, x03, x04. If you're ever in one of these equilibrium points, the system stops evolving, right? So the key is, what are these equilibrium points stable or unstable? And you can actually you can define stability for equilibrium points. This is an unstable equilibrium point because the system likes, if you just disturb it a little bit, it likes to get out of this equilibrium. You might find an equilibrium point that's stable, like this, where if you just move the system anywhere, it tends to return back to this equilibrium point. And you can find systems that are unstable in such a way that lead to limit cycles. In other words, any initial disturbance will get you out of this point, but if you try to get if you get too big, there's a force that pushes you back on. And this leads to what we call a limit cycle. Okay? And this is exactly what we want. We want equilibrium points that lead to limit cycles. Okay?
So it seems like what's in oscillator looks like a feedback loop in there. When the amplitude goes up, you have more damping factor comes back, and so on. So can you characterize this with feedback theories, with response time, phase margin, and such?
It's tough because it's not a linear system. So what you can do is you can linearize about a given operating point. So you can assume that you're in steady state oscillation, and then assume there's a small disturbance, and then derive an equivalent linear differential equation, or if you like, a linear equivalent circuit that describes how you return back to equilibrium. But the system is nonlinear, so you have to be, it's pretty tricky. You have to be very careful about the way you do it. Okay? So that's all I'd like to say about the detailed mathematics of oscillators. Obviously, we're going to ignore all the mathematical details. We're going to basically look at circuit topologies that have good properties and simulate them and verify that they work. Okay, so let's look at, let's summarize some of the BJT oscillator design equations. Okay, so let's say, just for argument's sake, let's say we want an oscillation amplitude of 100 millivolts. Call that V out. Okay? So that's a very typical spec, right? You might say I have a VCO, I want oscillation amplitude, I'm going to buffer it and then drive my mixers. And let's say you say I need 100 millivolts or a volt or 50 millivolts or whatever the case may be. Okay? So now the next thing that we choose, we know that we need a loop gain that's bigger than 1. Okay? So the question is how much bigger than 1? 10, 15, 100, 1.1, 1.01, right? So this is where engineering comes in. So an engineer says, well, the loop gain has to be bigger than 1 over process, over temperature, over everything. So why not make it, let's say 3, right? Seems like a very arbitrary choice. But in practice, you could say that 3 leads to a pretty good design. And this is you could think of this as a starting point. I'll choose a loop gain of 3, and then I'll run some simulations and see how the performance changes if I change the initial loop gain. But this is a good starting point. Now clearly you don't want to pick something too close to 1, right? You don't want to pick 1.1 because over process you might end up with a loop gain of 0.9 and then the thing doesn't oscillate. So clearly there should be a margin bigger than 1. Maybe the better number is 2. It depends on your particular process. Maybe it needs to be larger, 4 or 5. So think of this as a good starting point. Okay? So the next thing we do is we design our tank to resonate at omega naught. And here we have to be very careful to model all the loss in tank and all the loading effects. The tank is something sacred. You want to basically keep it as, this is my LC tank, you want to keep it as clean as possible, so avoid putting anything on this tank that would DQ it. And so obviously if you're going to drive a load, you have to buffer it so that that load, let's say it's a 50 ohm load, you're not going to put 50 ohms across here because that would DQ your tank. Remember, the Q of the tank is the RT over omega L. And so what you'd like to do is maximize this shunt resistance. In fact, what you'd like to do is not even put any explicit resistor here. Just let this be the total parasitic resistance of, say, the inductor and capacitor combination. Okay? And if you have feedback, as we saw last lecture, you have to be careful to include the loading due to feedback. So in the case of a transformer feedback that we looked at last lecture, the input impedance of the transformer appears at the tank through the transformer winding squared. So you have to make sure you include that. Okay. All right, so the next thing we do is we estimate bias current. And the reason you have to estimate this is there's a little bit of iteration. We know that the first harmonic current is roughly the desired amplitude over RT. But unfortunately, we don't really know RT because RT depends on IQ, right? Why is that? Well, remember our transistor, if I were to hook up a tank across the transistor, the output resistance is a function of IC, right? And the input impedance is also a function of IC or IB. And so if I have a transformer here, then I have to be careful to include the loading effects on the tank. Now hopefully the loading effects will be small. So if I first of all neglect the loading, calculate I omega 1, and then based on I omega 1 calculate IQ, the DC current, and then iterate a few times, very quickly I'll converge on the right value of RT. Okay? And if you guys do a homework assignment, this will become very clear as you do it Okay, does that make sense to everybody? Okay, now for a BJT, we have a relationship that I omega 1 is 2I1b I0b times IQ. So B is known, or basically at this point it'll become known because you're going to specify or set N. Because V out is known, V in is therefore known, therefore B is calculated. And so now I just substitute for B and solve for IQ. Okay. So pretty much you can see now that the design is done. So coming back to the circuit, IQ is known. There's going to be some parasitic capacitance here. I'm going to put in my tank, my inductor. I'm going to add some tank capacitance basically to dominate over the parasitic capacitance, because the parasitic capacitance will vary a lot over process. And then I design my feedback network, which is the N factor. Okay, and so you see there is some design freedom. You know, we had the freedom to choose N. In some ways we also had the freedom to choose VO. In some situations we don't. We need full rail-to-rail or close to it to get the best performance. But for now, let's just focus on the free parameters. So because there's so many design variables, we kind of just said if you outlined a procedure that if you fix VO and N, then everything is known. You can basically find all the components. Okay. All right, so if we go back to our full schematic, looks something like this. So I'm going to have a transformer winding here. Going to have bias voltage here, and I'm going to have an emitter capacitance here. So there's one important practical thing you need to be aware of. You need to make sure that this emitter capacitance is less than N times the tank capacitance. Okay? And that's to avoid squegging. Okay? This may be a new word to you. Squegging is, I'm sure some English person came up with this word. Sounds very English. Squegging is this phenomena where you basically observe your oscillator doing something like this. And Al talked about it in his lecture. The idea is that there's some kind of oscillation going on in your bias circuit. In other words, the amplitude grows, but because of the time constant of this bias circuit, the bias circuit is slowing the circuit too much down, and it can't basically go into steady state in time. And so before it's gone into steady state, the poles move basically back into the left half plane, and the oscillation dies. But as soon as it dies, right, the GM of the transistor gets bigger again, the poles move into the right half plane, and the amplitude comes alive again. And this keeps happening over and over again. Okay? Now it's fairly complicated, and I actually don't know how to derive this equation. I should think about it. But somebody's derived this relationship and tells you for this particular oscillator, keep CE less than N times CT, and the circuit works. Al, do you know how to derive this? Yeah. Yeah. Okay. Yeah, it's definitely the, you know, there's RC time constant with the GM of the transistor, yeah. Yeah. Okay. Kevin?
When we're growing in amplitude, that's when the loop gain is greater than 1, and when it's falling is less than 1, right?
That's right. Yeah.
Shouldn't GM be a continuous function of B out, so eventually the loop gain will be 1?
Well, what's happening is that the circuit can't reach steady state because remember that putting this resistor here tends to reject increases in current, right? And so this circuit, in order to work, it needs to have, let me show you a way of what happens. So let's say that, let's look at some typical so as I mentioned before, the current waveform, or the way that you inject energy into the tank, doesn't have to be continuous. You can actually inject current into your tank in a bursty manner. So this is the collector current. This is the collector current when IQ is fixed. So in fact, go into Mathematica and plot I1, basically I1B, I0B, IQ, and actually it's easier just to plot either the B cosine omega t and make B very large, right? And this is what the collector current looks like. So it's becoming very bursty, and so if you plot it for large B versus if you plot it for the bias current being limited, you get different waveforms, okay? And the idea is that if this bias circuit can't respond fast enough to keep the bias circuit constant, then it's hand wavy here, so bear with me. What's happening is that this peak has to be just right in order to make an energy balance happen, right? And if the circuit prevents the peak from getting too large, then you might not be able to deliver enough energy into the tank. So if that capacitor is too large and it doesn't let this peak go high enough, it will prevent you from going into steady state. You can never get enough energy.
So even if the loop gain becomes 1 for a small time, it won't be able to hold that state because of the...
Yeah. Yeah, I mean, very loosely you can think of it as a dynamic of a system. It basically, it's vacillating back and forth. It can't actually reach, it's an overdamped system, right? So it overshoots, keeps overshooting. But that's just intuition, right? Okay. So let's now look at another topology. Let's imagine a common base oscillator. Now, what we looked at up to now was common emitter oscillator. So common base oscillator is going to look very similar, except we're going to hook up our transistor as a common base amplifier. Okay, so I'll draw AC schematic first. So somehow I need to feed the output back into the input. And because a common base amplifier actually has no phase shift, if I use a transformer, so let me just use a transformer, I actually don't need to invert my signal. I can just do a feedback like this, okay? But the nice thing about a common base amplifier is actually, because you don't need a phase shift, you can use a capacitive transformer. So I can take my signal here, tap it, and feed back to the emitter node. So that I can use a cap transformer. And this is basically, it's more compact. It's IC compatible and works at higher frequencies than a transformer. So definitely this is a preferable way of designing an oscillator because it doesn't require the transformer. Okay? Questions? Yes, Debo.
So, is the transformer the only way to generate a 180-degree phase shift? Can't we hook up another amplifier, unity gain, say, which will...
You could. Come up with something. Maybe we'll name it the Debo oscillator. Generally, if you'd like to have as few devices as possible if you're building a high-frequency oscillator, because of noise, we'll talk about phase noise, and otherwise because of the delay. So if there's too much delay in the feedback network, the oscillation is going to move away from omega naught. So let me show you a picture. So let's plot the phase shift of the tank. So this is 0 degrees. At low frequency, it looks inductive. High frequency, it looks capacitive, right? And exactly here, it looks just resistive. Now let me assume, remember, for steady state amplitude of for steady state oscillation, I need this equation to be equal to 1, right? And let me imagine now that n is actually n e to the minus j phi. So there's some phase delay going through the feedback circuit. Then that phase delay has to get compensated, because now this is complex. This now needs to become complex, so that overall the loop gain is 0 degrees exactly, right? That means I'm going to have a little bit of phase advance from the tank to compensate for that phase delay. So my frequency is going to shift away from omega naught. So you might say, big deal. I'm not going to resonate exactly at omega naught. I can take that into account. Yeah, I find out that the best point to oscillate is right here where the slope is maximum. You don't want to get to a point where this slope gets small, because the ability for this circuit, its sensitivity to phase noise is very much related to the slope. The higher the slope is, the less sensitive it is to noise on the phase. And so if you want the circuit to have good phase noise performance, you want to oscillate omega naught. Okay.
Is the steepest point there also where you get the peak impedance from your resonant tank? So
That's also another point, yeah. So to maximize the oscillation amplitude and to minimize the power consumption, you'd also like to be at the peak. Okay? But if you have a clever circuit, bring it to class. Okay, so what do the design equations look like for the common base oscillator? Again, I have my tank. I have a resistance here that models the total tank resistance. And then I'm going to have a feedback network as follows. Now, does anyone notice a disadvantage to this oscillator compared to common emitter oscillator? What's that? Why is impedance matching an issue? Anybody? Think about the discussion we just had. We want to maximize this resistance, the total resistance seen at the output of the tank. That's right, yeah. So instead of, remember, in the common base oscillator, we're looking into the base. Common emitter oscillator, we're looking to the base, which is a high impedance. Now we're looking into the emitter, which is a low impedance. And that transformed loads our tank. So that means that I have to make my N ratio pretty big to avoid the loading. So now the loading from emitter loads the tank. So N can't be too small. Okay? And because this is a capacitive divider, N is just 1 plus C2 prime over C1, where C2 prime is C2 plus C pi of the transistor. Okay. So this is the AC equivalent circuit. The way we actually bias it up looks a little bit different. I'm going to bias it with a current source here. Again, I can have this capacitor here, and then I'm going to have capacitor to ground here, and this would go to a bias voltage. And you can see now that the bias current of this device is fixed by IQ. So the analysis that we did applies exactly the same. Okay? And you can see that this one is a lot more amenable to integration. It almost looks like something you could just pop into an integrated circuit. You got a current source here, got these capacitors. You can build these capacitors very easily in an integrated circuit process. You can use basically just the metal layers that you get for free and build up pretty nice capacitors here. You want to avoid using nonlinear capacitors, so you basically want to make these capacitors simple metal capacitors in order to, as we'll see, phase noise is very sensitive to nonlinear capacitors. Unfortunately, if you want to make a VCO, voltage controlled oscillator, you will have to make this a varactor, right? So this would be a PN junction varactor, and we'll talk more about VCOs later, about how to make sure that there is no noise injection from this port. Okay. Questions? All right. So what's cool about the Colpitts oscillator? Actually, yeah, we call this the Colpitts oscillator. Okay. What's cool about the Colpitts oscillator is that you can actually generate a whole family of oscillators by just moving the ground around. So let me show you how that works. So let's take this oscillator, and instead of grounding, so ACY is this point's grounded, and this point's grounded. Let's just connect all those points together. So I have the following circuit. So remember, this point is grounded, and this point is grounded. So now, this is a ungrounded Colpitts. And if I ground the base, I get the Colpitts oscillator that I just saw. But I could also ground the emitter, right? Or I can ground the collector. And the operation of the circuit shouldn't change in a fundamental way, right? A ground is just a ground. It's just a reference point. So in theory, I can just ground any point and produce another oscillator. And for a while, people were doing this without realizing it and inventing new oscillators. For instance, let's say we ground the emitter. Okay? So let me show that over here. If I ground the emitter, then this position now is floating, so this becomes a feedback tank like this. Have a cap from here to ground. That's this cap. And then this cap is from base to ground. Okay? So this is a grounded emitter. Well, what if I ground the collector? So again, same circuit. If I ground the collector, then you'll notice that the base goes through an inductor, again through an LC tank, to reach the collector point, which is grounded. And then on the emitter side, I have basically a capacitor from emitter to ground and a capacitor from emitter to base. So this is the capacitor from emitter to base. This is the capacitor from emitter to ground. So this is a grounded collector. And it's kind of cool because these oscillators at first seem to be very different devices, right? They seem to be very different beasts. One is an emitter follower acting like an amplifier. One's a common base amplifier. One's a common emitter amplifier. And yet they're all essentially the same oscillator. Okay? Questions? Yes?
So they operate the same? Like there's no difference on loading from the transistor or...
No, there is. That's the key point. Because when you ground a node, for instance here, I'm grounding the emitter. So obviously the emitter is not going to load my circuit. So where I place the ground will have a big impact on basically the loading and the feedback factor. But as far as the circuit goes, it's really the same circuit. The emitter points moved around. Okay?
What about leakage?
What's leakage?
Low leakage.
LO leakage. So by definition, this is an oscillator, so LO is everywhere, right? There is no leakage.
I mean, you have sharing the same ground with other.
Oh, I see what you mean. That's actually a very good point. So let's defer discussion, because here we're talking about circuits that, I mean, right now we're just talking about oscillators in general. Later on, we'll see, to build a robust oscillator, first of all, you'll probably go differential. So we could take all these circuits and turn them into differential equivalents to try to minimize basically supply noise and ground noise. Okay. Now there is a couple of, so let's look a little more specifically at some of these oscillators. I'm going to call the first one, the emitter grounded one, the Pierce oscillator. And the Pierce oscillator basically looks something like this. And remember, there's also this capacitor across the tank. Well, if you notice, what happens if I get rid of this capacitor? Will the circuit still work? In fact, it does. What happens is that from an AC circuit perspective, you can think of this as one series LC tank, or if you like, a parallel tank with this inductor in parallel with the series combination of these two inductors. So you can think of a big AC current flowing here, I omega 1, and that means that the output voltage is I omega 1, let's call this C1, times 1 over omega C1, and the input voltage will be the same current, I omega 1, times 1 over omega C2. I'm now assuming that the tank Q is high, so that the current of this transistor is actually a small fraction of I omega 1. Under those conditions, you can see that the N factor for this oscillator, which is V out over V in, is simply C2 over C1. And so the Pierce oscillator has some nice properties. Again, probably the nicest property of the Pierce oscillator is that you can stick a crystal right here and build a crystal oscillator. And we're going to talk about that a little bit later, but effectively you're using a crystal as a big inductor right here. Okay. The nice thing about doing that is that when you stick a crystal here, if you remove the crystal, this thing turns into a buffer. And so it gives you the option of either using this as a buffer or as a crystal. But I'll talk about that later. I don't want to confuse you guys. So how do we bias this guy? We can just bias it by putting a current source right here. Or if you like, a big resistor to supply. Of course, the impedance of this has to be very large because I don't want to load this tank. Right? Any resistance at this node tends to load this tank. Okay? Question?
The C1 and C2 has to be large enough to absorb the Miller cap across the baseline emitter? Okay.
Yeah, that's a good point. So you have some Miller cap. So C1 and C2 actually, because they're forming the tank, need to be large enough to pretty much dominate over all the parasitic capacitances in the device. The effect of the Miller cap is not so bad, because what it does is you can think of this cap in parallel with this inductance, right? So if the inductance dominates, basically this cap just changes the value of the inductor a little bit. Do you see what I mean?
Change varies over the cycle because the voltage changes on the collector.
Well, so if you have, so basically if I have an LC tank and I look at the perfect LC tank, this is what the reactance looks like, right? So this is resonance. So as long as I'm below resonance, the thing looks inductive, right? If I'm really below resonance, then this looks like a straight line. it looks almost like a perfect inductor. So as long as C mu is much smaller, right, so the resonant frequency is much higher than the frequency I'm operating at. So let's say this is omega naught, and this is the resonance of C mu plus L. If I'm operating over here, the effects of C mu are pretty negligible. Okay. Okay, let's look at the common collector oscillator in a little bit more detail. Okay, so the way the circuit looks now, I can draw the biasing. I can use a current source to bias it. And I have this LC tank. Okay, so now the first observation is that it's very similar to the Pierce oscillator. If I get rid of this capacitor, the circuit still works because I can form a resonant tank like so. In fact, this capacitor can just be moved in parallel with these capacitors, and you can think of this as one net capacitor. So there's no need to put an explicit capacitor here. You can just make these capacitors bigger to make the total tank work. So you get rid of this extra component, and then the circuit becomes very simple to think about, because again, under a high Q assumption, this tank current is much larger than the current that's being injected by this transistor, and so for all purposes, I omega 1 flows through here and produces an input voltage and an output voltage. Okay? So same kind of analysis we can apply to this oscillator. The other important point to note is that there's no reason to actually ground this. It doesn't affect the circuit operation if I put a resistor here. Assuming that resistor is not too large, so C mu doesn't come into play again. But if I put a resistor here, then I have a buffered output, kind of for free. I don't have to do anything to create this buffered output. So remember, you always need a buffer. So if I have an oscillator, which is, let's say, let me represent it as an LC tank, I can't just stick a voltage, a resistor here, let's say 50 ohms, because that'll DQ the tank. So in this case, I can't stick a resistor anywhere here because, you know, if I have a let's say this is driving a transmission line, I can't put the transmission line lead here because that would stick 50 ohms onto my tank. But I can put a 50 ohm load here, and as long as this voltage swing is not too big, it's not going to fundamentally change the performance of this. And so I have a buffered output available to me for free. I probably will buffer it more, but this built-in buffering helps. Okay? That makes sense to everybody? Okay. And there's another variation of this. The other variation is to think, well, I can think of this as a parallel tank, right? I can also, though, think of this as a series tank. What if I put a capacitor in series here, so that instead of here I put the cap in series, so now the tank is this inductor and then these three capacitors in series. If I do that, I get the clap oscillator. Okay, no need to clap for this invention. So here I'm going to put another capacitor here and ground it, and you say, well, big deal, why would you do that? Well, this is a nice way to actually build a variable oscillator. So here I can make, for instance, this isolation that I get for free, I can use to introduce a varactor. And so because the DC point here is basically will not disturb this circuit, I can vary this DC value because I have this cap isolation. So maybe I have a large resistor or something like that to bias this transistor up. Now I can change this DC value, which will change the capacitance here. So this becomes a variable capacitor, and that will change the resonant frequency of my tank, and so I get a VCO. Now there's nothing special about this clap oscillator. You can stick a varactor in any of these circuits. Anywhere you have your tank capacitor, you can introduce some varactor capacitance and you create a VCO. The only problem is you have to make sure that you can change the bias voltage on this varactor without disturbing the circuit. Okay? Yes.
This varactor diode capacitor, isn't this shorted at AC when the voltage is DC across diode? Isn't that shorted?
So this is reverse biased, right?
Yeah, so one end is ground, the other end is DC voltage.
Yeah, so let's say I put this at 1 volt.
So the omega O, it's shorted, AC wise, isn't it?
No, so this has a value. So the PN junction reverse bias capacitance is on the order of these caps. So it becomes part of the tank, right? So what do you mean by shorted?
Well, it's 1 volt is AC ground. It's zero
No,
volts.
oh yeah, I see your question. See, I drew a bad resistor here, but this is a resistor. I need to isolate. Yeah, good point. So basically you want to isolate DC voltage from the AC signal. Thank you. And the way you do that is you use a resistor here. Pretty large resistor. This might be a kilo ohm or something. You could also use a big inductor. So if you could, actually it's preferable to use a large inductor like this, because then the inductor introduces no noise into the circuit and it lets you bring in a DC voltage here, and the AC signals see a high impedance, so all the AC signals will go in this direction. Yeah, thank you. Okay, any other questions? Okay, so one more thing I'll mention is these. Let's talk a little bit about these varactors. Varactor is, of course, a variable capacitor, and there's two kinds of varactors. There's PN junction varactors, so I can use a PN junction. So the PN junction, in a typical process, let's say you have a P substrate, you would have an N well, and you would introduce, let's say, N plus junctions and a P plus junction here. So you would have a P plus N diode. So this is the P terminal, this is the N terminal. And the issue is that even though you get a nice diode from here to here, you also get a diode from the well to the substrate. And the substrate is resistive. Okay? Now let me also draw a zoom in of this structure. So this structure is N plus P plus, and so the actual capacitor happens over here, right? It's this depletion region. This is just the extra distance we have to move to get to this contact, right? So this introduces some series resistance. And this over here introduces another parasitic. So maybe the equivalent circuit that we can draw for this capacitor, draw it over here, is I have my cap, some resistance. This is the P, this is the N side, but then the N side also has some resistance and then some well capacitance and then some more resistance to ground. Okay? So if I'm going to use this diode in my oscillator, what I really want is the capability of changing the reverse bias voltage to change the capacitance, and I really would like to avoid putting this node on my tank, right? Because this node, if a voltage swings on this node, then current will go into this branch here, and basically you'll get loss through this resistor and this resistor. And so that will DQ the tank. So really I would like to ground this node. In other words, I'd like to choose an oscillator topology where this node doesn't move. So for instance, if I go back to, let's say, my Colpitts oscillator, this is going to be some fixed capacitance. I'm going to have my inductor, and then now I need to introduce my variable capacitance across here. Okay? And so now I have a choice. I can hook this up in several different ways. I could hook it up like this. I can hook it up like this. Right? So let's say that, and keep in mind, I want this to be reverse biased. So this point is at VDD. And so if I use this configuration, then it puts the, first of all, it would put the dirty node onto my tank. And second of all, I would need a voltage larger than VDD to reverse bias it, right? So if I use this configuration, then in order to reverse bias this, I'd have to use a voltage larger than VDD. That means I'd have to put a cap here to avoid connecting that here. And this dirty node is connected to my tank, right? So clearly the right way to do it is the other way. So if this is VDD, as long as this is below VDD, this is the V2 node, then the circuit will operate correctly. Okay. Questions? Okay. Well, obviously everything we've said about bipolar oscillators also applies to MOS oscillators. So all the topologies we've discussed more or less translate directly into MOS form. Few small things change. For instance, let's talk about let's take, for instance, this Colpitts and build it with a MOS device. Okay. So one of the things that you'll notice when you build one of these oscillators is, remember, at the very beginning of the lecture we found that the GM of this device, the large signal GM, should be N over RT. Okay? Now, because bipolar GM is much larger than MOS GM, and because the bipolar is much more nonlinear than the MOS, this is a question that David asked last lecture, what we find is that for a bipolar device, the GM curve might look something like this. So this is GM versus the oscillation amplitude. For MOS, it might look something like this. It's much more gentle. This is a compressed device, a MOS device. The GM as you increase the amplitude. That means that we can support much larger oscillation amplitudes. So MOS oscillators have much larger oscillation amplitudes. Okay? And that's actually a good thing, as we'll see later on. Of course, that comes at a cost. We might have to burn more current to get the initial loop gain. We still need to make sure that GM RT over N is bigger than 1. So because the GM of a MOS device is smaller, that generally means either pumping in more current or making this device larger. I can only make this device so large because then the parasitic capacitances of the device start to dominate over these external capacitors. So that means that eventually I have to just pump enough current through this device to make the initial loop gain sufficiently large. Okay. The other difference with MOS devices is that you hardly ever see people build oscillators like this. The most common way to build MOS oscillators is actually using a cross-coupled differential pair. So let's see why that is. Okay. So this is actually the building block that people use for MOS oscillators, right? So this is really just a diff pair. Let me redraw it as a diff pair. Where I've taken this output and connected it here, and taken this input and connected it to this output. Okay. So from a feedback perspective, the gain from here to here is positive, right? And so bringing this back is actually positive feedback. And the n factor is in fact 1, right? I'm just taking the output and connecting it back into the input. So this looks like positive feedback with n equals to 1. And so in fact, if you want to have another value of n, what can you do here? Just use a cap divider. So in fact, what's very common for a bipolar version of a cross-coupled pair, what you see is people doing something like this. So again, this is the same idea. I take the output, bring it back into the input, but but now I take a fraction of the output. So this is positive feedback with n basically bigger than 1. Okay? So now we could analyze this circuit just like we did before as a positive feedback system, but we're going to now analyze it as a negative resistance system. So the question is, remember, that we can analyze our oscillator as a lossy LC tank, say with conductance G, and a circuit that somehow or another creates a conductance minus G. And this is consistent with our energy balance perspective, because in our energy balance perspective, if this circuit is supplying energy, that means it has negative resistance, right? And we found for it to work, the negative resistance had to be exactly N over RT. Okay? And the reason that from a negative resistance perspective, the reason that this circuit is stable is that the resistance, let's say G of V, let me say the minus G of V versus V, where this is the oscillation amplitude, is some kind of decreasing function. So if initially we start out over here, initially when the oscillation amplitude is very small, this has a lot of negative resistance. And the negative resistance is more than enough. So G initial minus G initial, absolute value, is more than enough to compensate for the losses. But as the oscillation amplitude grows, the negative G compresses, and eventually it reaches a point where the losses in the tank are perfectly balanced by the negative resistance in here. And so that will be our steady state oscillation amplitude. Okay? So this is an equivalent perspective for how an oscillator works. The neat thing about this negative resistance perspective is that I'm not explicitly talking anywhere about feedback. Okay? I'm just saying that I have a circuit here. Somehow it generates negative resistance. For instance, a very common way to do this at very high frequencies is to use a tunneling diode. A tunneling diode, you know, it's not a feedback circuit, it's just a two-port element. But it generates negative resistance. And so I can use that negative resistance to compensate for the loss in this tank. So in some ways the negative resistance perspective is slightly more general because it allows us to use two-port devices also, one-port devices to build oscillators as opposed to a two-port amplifier. Okay? So let me just show you guys how this works. Let's go back to the very first study. So I'm going to hook up a voltage source here, let's say Vx, and then I'm going to measure the current Ix flowing into this circuit. And to first order, the current Ix is equal to Gm times the input, right? And the input is actually the output divided by n through this transformer, but inverted. Okay? So the conductance looking into here, so this is inverted. So then you can see that the conductance looking into the circuit, which is Ix over Vx, is minus Gm over n. So, in fact, this perspective is consistent that this feedback is generating a negative resistance. Okay? And now the design criteria is very simple, because I can say, if I hook up RT here, let's say with some capacitance, and if this is Gx, then what I would like is for Gx to be larger than 1 over RT. So this will guarantee basically right half plane pulse, or net negative conductance. Okay? Well, that means that, so let me take absolute value, because I know that this is going to be negative. I just found that Gx is Gm over n, and that should be equal to greater than 1 over RT. In other words, that Gm RT over n should be bigger than 1. And remember, this is just the loop gain. So this feedback perspective is really, in this case, equivalent to this negative resistance perspective. Okay? All right, we'll pick this up next Tuesday.